I'm going to open the source code from last time. If you remember, we had this small application here, this hello world and a little bit drawing on the canvas. I'm going to open it. I'm going to rename the file with canvas experiments. So it's going to be a new title here. Okay, font size bigger. Attract my attention if something like this is problematic. And what I'm actually going to do, I'm going to comment out most of this code. Today we start off from scratch, so this was just like a demonstration, a hello world idea, but now we have a blank canvas. We start from zero and start to experiment what it can do. And our first task is going to be to draw this house. So today I'm going to draw a house on a canvas. Now, I tried my best. It looks like a house, but yeah. First thing to notice is, let's look at the overall shape. So let's not consider color for the moment. And there are a few points that are interesting here. I have marked them with coordinates like this minus 50-50 over here, so this is our center of the axis, 50-50, 50 minus 20, minus 50 minus 20, and 0 minus 60. So remember that the axes on a computer, the y-axis goes down, so it grows downwards. It's a little different than what you do in math class. Okay, but let's try to do this small drawing. I'm going to zoom in a little bit, and I'm going to go back and forth to see these those 4 coordinates. Okay, some other coordinates that will appear later are a bit messing. So okay, and let's try to draw it. So it's a good idea to be modular. I'm going to draw a house, so I'm going to make a function that's called drawHouse. And I'm going to give it the parameter, the canvas that we're going to draw it on. So this is important because maybe we will have multiple canvases in our application. And I'm going to define this function here. And with the canvas parameter. And first thing to do is, from the canvas, we are going to get our context. So the context is the object that will allow us to draw on it. And this getContext function has some parameter here. I'm going to specify 2D. It's also possible to draw 3D items on the canvas, but we won't experiment with that too much in this course. But feel free to play around with it. And now I'm going to reuse part of this old code. So first things first, this begin path tells it that I'm going to have to draw something, start to draw something. And I'm going to take this move to line 2 and stroke functions from here, paste them down. But first coordinate is, let's say, minus 50-50. Okay, we are going to start in this lower left corner. So move to minus 50-50. Then I want the first line to go to 50-50. And a few more lines, right? 50 minus 20. And minus 50 minus 20. And now I want to close the wall part. So this part here, I'm going to have to draw another line to minus 50-50 here. Otherwise, this line will not exist. So I prefer to copy this move to and then rename it to line 2. It's just how I write code. Okay, so this part here, it looks very cryptic. Good idea to make a comment here and say the wall. Well, the wall, the one we see. Okay, I'm going to copy this and make the roof. So quite easy. Again, I'm going to start with, let's say, -50, -20. 50 -20. Go up to the pointy part, 0 -60. And back to the beginning to complete the roof. So I have to go back down to -50, -20 with a line to and do the stroke. Okay? Should be clear enough. Now, I did something here. We also have coordinates for the door and coordinates for the window. It's going to be pretty much the same thing all over again. So I'm going to copy this wall code again, rename the comment as a door, and it's going to be -30, 50. It's a little tedious. You have to kind of do this for a while. -10, 50, -10, -10. And then -30, 10. Sorry, this was not -10. -30, 10. And lastly, go back to the beginning to close the door, literally speaking. And last but not least, the window, so 10, 20. $40, 20. 40 -10. 10 -10. And we close it with the first one from the beginning, and we are done. It should work now. I'm going to save the file. I'm going to go back to the web page, refresh the page, and nothing seems to happen. Console C is not defined. Okay, console, you open the console pressing F12 on the keyboard. You can also open it, I think, by going here to these dots, more tools, developer tools, or Control-Shift-I. On a Mac, probably Command. Some of you guys have Macs there. And again, for last time, I'm using Google Chrome here, but these consoles are available in all modern browsers. And usually F12 is going to open it. Okay, so C is not defined. If I click here, it's going to tell me which is the C. And yes, because I copied this code in Rush here, C was my variable for the canvas before, so I'm going to have to rename it with the parameter I gave to the function. Now, going back here, refresh, and this is our house. Okay, so our house is here because our coordinate system center is here. So more or less what happened when we tried to display it, we display this region here. And it contains just a part of the house. So we will need to translate the house. Okay, we will need to move the house to the middle of the stage that we want to visualize. And last time, one of you, I don't remember, maybe it was you, told me, but why do you have to translate? Can't you do it some other way? And I said no, but meanwhile I found out that yes. You can translate the canvas instead. Move the canvas before you do the drawing, then do the drawing, then move the canvas back. It's somehow a bit out of the ordinary, but it's possible. You can actually do that. And we will experiment with both of the things just to see how that would look like. So for example, in the beginning I could say context translate to 150, 150. I remember that our canvas size is 300 by 300. So translate there first, do the drawing, and then it's a good idea to translate back, because otherwise your coordinate system is going to be shifted throughout your rest of the drawings, which may or may not appear. So I'm going to I'm going to save this file, go back here, and this is our house, and apparently I made some mistake. Okay, I wonder where it is. It's a very strange mistake. Let's look a little bit. So the wall, 50. Okay, maybe this one. Yeah, it needs here minus 20. This minus 50, 20 didn't exist. I think that was... Yeah. Okay. Fantastic. We have a house. Okay. Now, it's also possible to add the colors. We initially had some colors here, right? Okay. Light blue window, brown door. Okay, so I'm going to go the door, context, the function is fill style, I think. I don't remember exactly.
Actually, the door, I think it's the window.
Oh, I'm sorry. I didn't modify the comment there. Very good, thanks. So window was light blue. I'm just going to type in there light blue. And I will, in addition to the stroke, I will also want to fill the element that was drawn. So I will have to tell the context to fill as well as to stroke. If I just tell fill, it will not have the contour, the boundaries. Okay, so I'm going to move fill below the fill style because it's easier for me to copy this. And now I'm going to say brown here, right? Very, very nice. It recognizes those things. The roof is red. Another way to type colors in HTML is by the hex value. So I'm going to say FF0000 stands for red, stands for green, stands for blue. And another way to write colors here is to say RGB, open your parentheses, and say, I want blue, right? So no red, no green, 255 is the maximum value of blue, and 255 is equal to FF in base 60, right? Okay, so let's see now what happens. I forgot to copy my fill function. Beautiful. Yes, we have the house. It's great. Okay, but even though this hack of translating is really nice, and funnily enough, you can do even more powerful things with this method. For example, I could rotate. I'm going to rotate the canvas by, let's say, math pi. So by pi divided by 4, what will happen?
45 degrees.
45 degrees.
To the right.
Well, yes, because, well, you know your trigonometry, that's good. So you can even rotate this. And if I would want to rotate this manually without relying on the built-in functions from the canvas, I would need to recalculate coordinates for this that are rotated 45 degrees, and that's very, very difficult to do. Well, not very difficult, but more complicated to implement yourself. So this is a useful tool, but I'm going to rename this function draw a house by translating the canvas, but we are not going to use this. You can play around with this canvas moving as much as you want. Now you have the information here to do it. I'm going to make the drawHouse function translates the object itself, because I think it's quite important to learn about translation and about vectors. We'll see soon what that is. But more or less, what it's going to mean for us is that we will need the parameter location here, okay? And we are going to tell our function, draw it on the canvas, C as I call it there, at the location, and I'm going to use a vector for that. 150, 150. So I specified the location here as a parameter. And now, what we also need to do is add the first component of the location to all the x's, and the second component of the location to all the y's. So I will have to do this for a while, but the result will be more or less the same. It's just another way to do it. It's not relying on these canvas tricks. The reason why I'm telling you this is that these tricks happened to work in JavaScript and with the HTML canvas, but if you're going to work with something else, some other programming language, some other environment, they may not be available there. This is a very common practice to do, and it's going to work everywhere. So I'm going to refresh now this page, and our house appears again in the center of the stage as before. Now, you're probably not going to like what I'm going to do next. I'm going to comment out this function. What I did before is I saved this image as a PNG on my computer. Okay, I drew the house in PowerPoint or Paint or whatever, and I'm going to teach you how to just draw that house. That is a picture, an image. So more or less all that work that we did now could be done by just a few lines of code without messing with the coordinates or whatever. So our function draw house as an image is going to take a canvas as the parameter and the location where we want to put it as the parameter, same as before. And again, we have to initialize our context. And we need to define an image object. So this is available in JavaScript. And put our source, img.src, equal to house.png. So our house is actually here. So it's in the same directory as this file we are writing right now. And then we have to say it takes a little time for this image to load. So unload, I'm going to tell it what to do, and I'm going to tell it to put on the context to draw the image, the IMG image, at the location and I'm going to give it also a size, let's say 100 pixels. Okay, so now I'm going to draw the image as a house, the house as an image, and let's see if it's any different than before. Okay, problem is this is the center where I told it to draw it, but this is also the anchor point for the image. So if I would like it to look exactly as before, I would put here minus size divided by 2. And here also minus size multiplied by 0.5. Same thing, right? No trickery. So I will move it halfway to the left, halfway to the top of its size. And this is going to look pretty much the same as before. So now the question is, why would you ever do the complicated way when you can do the easy way? And this is what I'm going to attempt to answer to you now. by going back to our original function, this one, where I'm drawing the house. Okay? And I'm going to refresh, so now it's back to our vector design. First reason, you can make it any size you want. And I'm going to teach you how to do that. So let's say that we want this one to have a size of 1, so our unit size of 1. And I'm going to draw another house a little bit more up, so y of, let's say, 80 with the size of 0.4. We need to modify now our house function to include the size. Okay? And how you scale these vectors, you multiply each of these coordinates by the size. Okay? So now I'm going to have to put multiplied by size everywhere I see a fixed number in this. If it's 1, nothing will change. So our first draw house function is going to stay exactly the same. But the one where we said there multiplied by 0.4, that's going to scale all these sizes by 0.4, and our house will appear smaller. It will still look the same, but just smaller, right? Okay. So another smaller house on top of the first house. Of course, you could resize the image as well. But when you resize the image, artifacts appear. You know, if you zoom in too much to the image, you will start to see blurriness around the edges. This one will never have blurriness around the edges, even if you're going to make your image really, really big, like let's say 2 here. It will still be as sharp as before. You can even make it 20, but more or less you're going to see just okay. But no blurriness happens here. If I would try that with the other image, blurriness will appear, but these projectors are not very good at showing it, so I'm not going to bother. You already know that that happens in real life. Okay, another reason for doing it programmatically, we will try just in a second. But first, let's put more houses, okay? I like houses. So I'm going to modify here the coordinates a little bit, and I'm going to do my best to not overlap them. Let's say something like that. Okay, and let's make another row of houses a little bit more down on the y-axis. Okay, maybe that's good. And shift these a little bit. So now I'm just trying to draw a picture of a village or something. And yeah, this would need more here, I think, something like that. And let's just put 2 houses in the front size. So these ones that are going to be lower, they are also going to be slightly bigger. I'm going to put 0.7, and I'm going to leave 2 full ones in the front line, maybe at, let's say, 90 and 190. So, okay, not very great. I mean, I would like these a bit more down. So I'm going to put maybe 190 here, and I'm also going to move this one to 210, so a little bit more to the right. Okay, looks kind of like a village. But how about we make it look different? I mean, not all houses look the same. So this is now going to be the true power of this method. So how about the color? Okay, color. Let's make a random color for each part of the house. So random color, this function is quite simple here if we look at it. So returning some string for looking like RGB 00255. you could probably figure out that if I'm going to write a function for get random color, and if I return something like RGB blah blah blah, but here I'm going to concatenate a variable for red, a variable for blue, green, and a variable for blue, and if these variables are random variables, random gives you between 0 and 1, okay? But if I need between 0 and 255, I scale it by 255, and I don't want 110.7. So I'm gonna round it also. Then you can guess that this is going to output for me random values of colors. And of course I could take this get random color and let's put it here inside the function draw house in the wall component, and if I refresh this, each wall is going to have a random color. And if I refresh the page multiple times, every time I'm going to get a different village. But this is not the way I want to do it. This is not enough control from my point of view. I could put the color of the house here as a parameter. But if I want to change more properties, like the color of the wall, the color of the something else, good idea to group them, encapsulate them all in a single object, and pass that parameter to the function of the draw house, and here take the value of the wall color and display it. Now this parameter has to come before each house, so var parameter equal to, and it's going to be an object that has a value for wall color. I'm going to define wall color column, this is the syntax here, get random color, yeah, and this parameter is now going to need to go to each of these functions. So the reason why this is a good idea is because I can still call the first value here, if I want, with the wall color of blue anytime I want. So it's not the whole village necessarily random. I can still have my initial house if I want. I have control over this parameter, even though it's random here. And now it's actually not going to be random because I'm giving exactly the same parameter everywhere. It's going to have a random color, but once it's set, all of them get the same value. So I will need to generate parameters, a new function, so very good idea to be modular. Function generate parameters, and very good idea to be specific, house parameters. And here I'm going to return something with the wall color, get random color, but let's add more. So let's add roof color. Okay. And let's add a few Boolean ones. Show window. Maybe it's not going to be a house with a window. Maybe it doesn't have a window. Maybe the window's on the other side. Or maybe it's a barn. Okay. And this, let's say it again random. So math random. I'm going to just give it equal probability to appear or not to appear. So if the random value is less than 0.5, then I want it to say true. Otherwise, false. I don't know if you're familiar with the syntax, but I avoid writing an if statement. So If this is less than 0.5, true, otherwise false. And same show door. Okay, same kind of thing. And now I have to handle these parameters also in our drawHouse function. So our drawHouse function at the moment can only do this thing for the wall, but I also have now door color somewhere. Yeah, the door. Oh no, sorry, it was the roof color. Here. So parameter roof color. And here I need to decide, do I show the door or not? So if parameter show door is true, I'm going to show the door. Otherwise, this code does not execute. Does not execute, and the house will not have a door. And the same will go for the window. Show window. Okay, if I refresh this, I'm going to get an error. Our generate parameters function, I renamed it to generate house parameters, but I forgot to rename it in the function call. So here, generate house parameters. So now it is going to work. The parameters may or may not. Okay. Yeah.
Not 0.5.
Okay, sorry?
The probability of less than 0.5 is like kind of function.
Yeah, it's. I think it's good. But again, as before, I want to have different parameters for different random parameters for each house. So this is something that I wanted to get to in this demonstration. So now when I refresh, some houses have windows, some houses have doors, some have both, some have none. Colors are different. I can go more. I can make the roof more pointy. I can make it whatever. And this is going to be your first exercise task. If you remember in your exercises, I mentioned fractals, and you can stick to that. Alternatively, you can make a very more realistic scene than this. Add more objects, define more things there, trees, whatever, sky, clouds, sun, anything. Make it look really nice. Make it random. Every time I refresh, I want to see a different scenery. You can also experiment with locations. So now my location is fixed. I want to see as much randomness, but still keep it looking good. Okay? If you can add animation to this, you get maximum points. Animation we study after a few minutes. But animation would be maybe draw a tree and maybe have that tree blow in the wind, or maybe have the sun glowing or something. So if the scene even moves while I'm looking at it, then maximum points. And before we finish, I want to teach you one more trick. Very simple parameter, it's the blur. So actually, it's possible to define a value for how blurry you want the house to look like. So let's say here I'm going to put a blur of 4 for the first 3 houses. Okay? I'm going to set the blur value to 2 for the next 3 houses. And for the last 3 houses, I'm going to put a blur of 0. Now our drawHouse function could take the blur parameter, and all you have to do is tell the context something. Tell it filter equal to, and this is a string, blur open parentheses, and here you could say, for example, 2 and close the parentheses, but I want to give it, concatenate the value from the parameters, so blur. And with this effect, if I refresh, it will not work. I know why. So draw a house. Oh, it needs to be in pixels. So this pixels, px here, has to be written. So now the houses in the background look more blurry. The houses in the front look more sharp. This is again something that you can experiment with to get more photorealistic effects here. This is extreme maybe to give you, so you can see it on this screen, but play around with these parameters. I think you can do many nice things. Okay. Questions about these parts? Fantastic. Everything is clear, or everyone is confused. Okay. Now, another experiment. I will make a new canvas. I'm going to rename this canvas Canvas A, make a new canvas Canvas B. I don't want to just get rid of my houses. I worked so much on them. I want to have them on all the time. So they are going to be there. And here we make new stuff. Now, look at this mess, this main function here. It's like complicated. Draw houses on the canvas. I think it's all we need to give it. I'm going to copy all of these code, make a new function, draw houses on a canvas, and then, oh, damn. Okay, I'm going to rename this canvas as C. It's a mistake. I would never name variables just by one letter. They can be confusing, but for quickness now, let's leave it like that. So, yeah, draw houses, C. And now we need to initialize the second canvas also to be 300 times 300. The context needs to know this size. So I'm going to have to also do this for B. But you can see, again, much code coming here. I don't like that. It's duplicate, it's double code. Not good. So function initialize canvas, and I'm going to give it a canvas ID. So this is a string. And our canvas ID is more or less going to go here. It's going to take the 2D context. The size, I don't agree with that. Let's say width, height. No point to use any global variables in this function. It's going to create problems if your employer or whatever tells you, but I want a bigger canvas. Okay, and after the canvas is initialized, what did I do? Okay, something very bad happened. Okay, it got better. Sorry about that. I have to return it. So I'm going to say now here, instead of this messy code, var c is equal to initialize canvas, canvas A, with 300 and 300, and I'm going to just delete this, and then our C variable is going to get canvas B. So much neater code, much clearer what is happening here. First canvas, draw the houses on it. Second canvas, animate polygons on it. Okay, that's going to be something new that we try now. Function animate polygons canvas, save the file, refresh the page, everything still works. But the code is easier to read. Most of the time, you're not writing code for yourself. You're writing code for other people. If they don't have to read full pages of documentation and you can understand the things from just reading the function names alone, that's your goal. Here, my only comments are at the wall, the roof, the whatever. I could have exported those as separate functions, but I'm not going to draw a wall on something else or a roof on something else than a house. I decided to group it there. You can be modular and export it. There's nothing wrong about that. But I needed to put the comments here. Otherwise, if you just look at this code without hearing my talk today, you will have no idea what is happening. What is this stuff? Size, location 0, minus 50. People are like, not for me. Too difficult. Okay. So comments, you don't need to put many if your functions are very well named. Yeah. And your code is modular. Okay. So animate polygons. Last time we experimented with this function draw polygon, and I think that now I don't need this code anymore there. It was left over from last time. So this draw polygon function, it's improperly named. I'm going to rename it to draw regular polygon. Okay. This was drawing regular polygons on the screen. What? Okay, cannot get read property, get context of null. Yeah. So the problem is our bad function that I wrote really quickly last time does not have the canvas as a parameter. It takes it as a global variable, and our canvas does not exist anymore. The ID canvas doesn't exist. Now we have canvas A and canvas B. So idea is we need to define here canvas, and when we are going to call our function for animating, for drawing the polygon here, pass it so that the function knows where to put the polygon. Okay. Still error, also in the same function, C does not exist. Our canvas was called C before. I have to have it the same name as in the Okay, so that's what we had last time. 2 polygons here. Okay, one that is actually a square. So this is coming from this function call. This radius, as I called it, it just means the distance from here to here is 100 pixels. And 4 tells me I want 4 sides. 8 tells me I want an octagon. 12 tells me I want a dodecagon, and so on. So now I'm going to get a dodecagon, and I see a bug. It's not closing. And the reason why it's not closing is actually very technical. And I will try to explain, but you really would need to practice these things by yourself and be convinced more or less. Okay. The unit circle. It's called a unit circle because this is 1. The radius is 1. Okay. If I take any point on this circle, alpha, at an angle alpha, any angle I get, I can calculate x and y. I can know where the point is going to be in the 2D space, x and y, relative to our origin, if I know the alpha and I know that the radius is 1. Two triangles there, you should see them. Here, the value for x, okay, the value for x is going to be what in this triangle here? The radius is 1.
Cosine of alpha.
Cosine of alpha, yeah. And the value of y? Sine of alpha. So this should be familiar to you. If not, the value of this, the x here, so the value of alpha is actually hypotenuse divided by the nearby value there. So that is the cosine. You should remember these from high school. If not, Google square, triangle, cosine, sine, and study a little bit. Okay, so back to our function. What I did last time in a really big, really fast pace is something that maybe should have been done a little differently. So note that now my translation is hard-coded. So our regular polygon is going to be drawn on a canvas at the location I want to be able to draw the polygon somewhere else. Now it's just always going to be at 100 and 100. So our location of 0 and location of 1 and cosine of I, so this is our alpha, I is our alpha, and I took all the angles from 0 to 2 pi, from 0, pi divided by 4, pi pi divided by 2, yeah, thanks, pi, 3 and 1.5 pi, 2 pi, so 2 pi is 0, but I went all these angles at a pace relative to pi divided by these sides divided by 2. So if I don't put this divided by 2, our polygon is going to have twice as many sides. You can think about this a little. And our start location should actually be, this move to, should actually be written the same way. But our initial angle is 0. Okay? I'm going to have here x and y. And to be absolutely sure that the function will close, you have to draw another line to the initial starting point, the last one here. And I will tell you why in just a second. So let's first do it. So line to the initial x and y. I'm going to refresh now the page, and errors. No errors. What is it?
Excuse me.
Yes.
Do you want to? Don't you give any pauses?
I do. Just in 1 second I give a pause.
Okay.
I finish this to work and then we have a pause. This location here, I messed up now the parameters. So I want our polygon to be at still at 1. Okay, let's put it right in the middle, 150, 150. So I added the location parameter to the polygon. And now that one closes. So the reason why it doesn't close, when you add these pi divided by sides here, floating point numbers in JavaScript have an accuracy. When you start to add different floating point numbers, sometimes the rounding goes up, sometimes the rounding goes down. In the last step of this for loop, you may not reach equal to math pi multiplied by 2. You may be a little before it, or in a little after it. If you end up a little bit before it, the after will exceed and you will not complete the loop. It's technical, you can think about it, experiment with it. It should be convincing enough, like that. Yes?
If we're starting from var x, location of 0 plus math cosine of 0, wouldn't it be more optimal to start in the for loop from I math pi math.pi is divided by sides, because the first one repeats itself?
Very good. So if I start in the first increment from here, the result is going to be exactly the same, but I do one less line 2. The first line 2, if I have 0 here, would be a line 2 from the same point to the same point. So it doesn't look like anything, but the computer will do extra work. We don't want to burden the computer.
Yeah.
Okay, very good. I think now we can have a break. Let's have a 10-minute break. So let's start again. And I close some other files that I opened meanwhile. Okay, back to our regular polygon function here. And like Cosmin said, this start can start here, and then it's a little bit more efficient. And it still works, it looks the same. But I called our main function where I'm drawing these polygons animate polygons. This is not animating any polygon. This is drawing polygons. So where does the animation come in? This is now question. One property I could animate here very easily is the size. So each of these is 100. I could also animate this. I could also animate the number of sides. These are all properties that I could animate. Animation means draw a sequence of images one after another really quickly so that your eye perceives movement. Okay? I'm going to comment out 2 of these functions, and I'm going to draw a regular polygon, a square, with varying size, starting at 100 and shrinking really quickly. How quickly? Set interval, and now I'm going to define a function here, what to do at this interval every 1000 milliseconds. Every 1 second. So every second, gonna draw a regular polygon with the size. And after it draws it, and after it draws it, the size shrinks a little bit. Okay? I'm gonna save this file, refresh the page, and get errors. Unexpected token something.
You forgot the parentheses, like regular parentheses.
Oh, yes, thank you. I forgot the correct syntax is like this. The function has no parameters. Now this here, I will get back to this syntax here in a second. But refresh the page. Okay, our square is shrinking. It's getting thicker.
It's withdrawing.
So the canvas keeps in memory the old square, draws the new square, but doesn't delete the old square. It's still animating. It's not shrinking. It's getting thicker. But that's not what I intended to do. What you want to do is clear canvas every time before you draw the new polygon. But our clear canvas function doesn't exist. So function clear canvas, you need to canvas is a parameter, you need to get the context and call the function clear rect. Rect is for rectangle, starting at 0, ending at 0, 0 x and y, and the width was 300, 300. This I think you can also get from this, but let's just do that. Save the file, refresh the page, error, and error that is coming here every second. Okay, so this haunts me now, this C here. I should replace all C's with canvas, but if I do that, all my code will get messy. So I'm not going to do that. Okay, now it's getting smaller very slowly. Too slow for the eye to really consider it animation. I replaced this 1000 milliseconds with 100 milliseconds, and the effect is more obvious. So now our square is getting smaller. Okay? And then it starts to grow. Negative sizes in our function equal to symmetry. Symmetry opposite from the center of the axis. You can think about this later. I'm not going to quiz you on it, but interesting effect anyway. Okay, what else could we animate? Of course I could animate the location. Let's say y location equal to 150, and I could say that I want the y location to also get smaller, and now our square gets smaller but at the same time moves up. And interestingly, this point here doesn't seem to move because this, how to say, it's moving up at the same rate that it is resizing. But you see the effect is different. So if my size would not decrease anymore and I just move the y location, this would be moving simply upward without rotation. But interesting effects that you can make with combining these parameters. Now, one more thing I want to tell is rotation. So we said before it's difficult, but actually not very difficult. I'm going to put here rotation parameter equal to 0, and I'm going to increase the rotation by a small factor. Let's say 0. Or keep it in terms of pi. It's nice. You should know why, but I want when it finishes a cycle to be exactly in the same place as it was before. If it's a factor of pi, of 2 pi at least, it's going to be like that. Okay, now our draw regular polygon, how do I update this to include rotation? Well, no. I add to the angle. So our initial angle of 0, no, you will start at the angle of rotation. All our eye angles here will add the value of the rotation, and our 0 at the end will add the value of rotation. It should make sense to you. So all the points that were used to draw the polygon will have to rotate by the amount I specify here. So now the square rotates. Okay? Square rotates quite nicely. I go back to my animate polygons. It should be polygons. Okay. Now these values I don't change anymore. They were just for demo. Here I wanted to show that you can animate many things. But now I really like this location. So I'm going to put more polygons here. maybe have a size of 8, and maybe a size of 16, all of them rotating quite nicely, okay? And I'm going to have the same thing inside it. So the size, I'm just going to make smaller. So here I want a size of 100 and here a size of 70. And I want the rotation to be backwards, minus the rotation angle. Okay? And now I have some more interesting effect happening there. So if you remember in the first lecture I mentioned some kind of superhero movie things, and something to do with Doctor Strange will happen in the future, but this is unrelated to that. But one of the things that he can do is generate these shields, some kind of effects where he blocks attacks from other people. It kind of looks like that, but it moves according to his hand. So it's After Effects or whatever, but here we're gonna, this kind of looks like that. But it moves. So let's learn also how to make it move with the mouse. Now it's stationary there, okay? I'm gonna use a global variable for this. Polygons location equal to, in the beginning I have this 150, 150, so in the middle of our canvas. So this is now polygons location. And I want the canvas to recognize when I click on it. And the way you do this is you write C, add event listener. I'm going to say here mouse down for now, and then function E. I will explain these things at some point, but bear with me. And then the polygon location, I need a function to get it. And that function is going to be get cursor position of E, and I have to implement that function. So it's not existing. Function, I'm moving this up so you see better. Get cursor position of this, it's an event, so I'm going to call it event. The canvas is actually one parameter of this event. And I can retrieve it with event.target. Now, if you want to see all the properties in this event console log function, it will log in the web console all the properties of this, and target is one of them. I found out that it's the canvas element there by doing that log. I will show you soon. And then what you want to do is get the bounding rectangle of the canvas. These functions I know because I have studied pages like that W3 schools, or more or less the documentation of the canvas element. You can learn many things by just Googling. Okay, we talked about it last time much, and we saw how to Google things. So check the video if you haven't. And we take the X value as event client X minus the left offset of this rectangle, and the Y is going to be client Y minus rect top. And I'm going to return XY as an array. So the cursor position is going to be an array with the x and y value. A bit technical here, but I'm not going to explain it more than that. So if you want more, study more. If not, use this function. It will work for you. I'm going to go back here, and when I click on something, this is my console log event. So from here, I learned that that target is actually canvas B. So I didn't need to send the canvas parameter specifically to this function. It was already there. I'm going to leave the console log so you know how to print things here. You can print anything. It's quite nice. And it moves. Yeah. So now it moves whenever I'm clicking on the screen. I could even call it, instead of mouse down, on mouse move. So now when I'm moving the mouse, it follows my mouse. So if you would like to have an effect where you use a webcam and you're moving your hand like that, and that thing moves with your hand, all you have to do is replace the mouse move with a very complicated function that detects your hand and moves it, which we will study in another week. Okay? Okay, but I'm going to leave this back to mouse down, and probably we will never look at this experiment again. It's just for you to learn. I don't think I will use this thing again, but study it. It's very important. And lastly, we will make one more experiment today. Let's see how it goes. It's going to be a little bit physics related. I'm going to say animate particles. Animate particles, a new function in a new canvas, canvas C. So canvas C, function animate particles on a canvas. I save the file, I refresh. Very good idea to do this very often, because it's you don't make many mistakes. If you write all the code in one shot, then the errors in the console will be overwhelming. So step by step is a good idea to debug like that. Okay, I'm gonna do a trick here, and I'm gonna move canvas C over canvas B, because I don't want to move down this every time I look at the new place I'm going to draw. So this is gonna be the new place I'm going to draw stuff. Okay, I want particles, small polygons, small circles or whatever, to move around in the screen independently, like having a life of their own. And that's what we are going to try to do. So let's first draw them, these particles. I'm going to put 50 of them. So draw, animate 50 particles. And what I'm going to do is, well, I'm going to draw them at random locations, more or less. So I'm going to use the draw regular polygon, but my size is going to be really small, like 3. At 3, you don't even recognize that it's a square or something else. If I put here 8 sides, it's going to look like a circle. So let's just leave this function there. Where to put them? Location. And rotation, I don't want rotation. It can be 0. Or I don't have to specify it. I think I don't even have to specify it. Let's see if it will work. And our location should be random. So location equal to the array containing random multiplied by 300, because I want the particle to be in our 300 times 300 square. And the same for the y. I save the file and I refresh the page. And nothing happens. And I don't know why. Console log. Does this work?
This is canvas name, right? Should be canvas C.
Yes, it should be canvas C. And this one here is canvas C if you look now at this small text on top there. Yeah, but I refresh, that text appears, so that's fantastic. But this draw regular polygon, I'm going to try here put the rotation of 0. Okay, so for some reason undefined rotation causes a big problem. If I still want not to have not to define that parameter, I could say here a default value for rotation equal to 0. And now the functions are going to work. So I'm going to animate the particles. I don't need the rotations anymore, and it works. Now nothing is animating yet. I said that the particles should have a life of their own. So each particle should know its place and where it's going. And for that, we're going to practice object-oriented programming. You don't have to do that. You don't have to use object-oriented programming here, but it's a very good skill to have, and some applications are just meant for that, to be used. So let's see how that looks. Instead of just drawing polygons, I'm actually going to make a class called particle. Okay, now this particle is going to have a constructor, a location parameter, and when the location is given to the particle, it's going to store it in its own variable called location here. So every time I'm going to access a particle's location, it will be that. But I also want to give it a vector for moving, a velocity vector, a vector that says which way to go, which way to move. I'm going to store this like that. And well, I could define here more methods. For example, a draw method on a canvas, and then say that to draw a particle, you need to draw a regular polygon on the canvas at the particle's location with a radius 5 and 8 sides are enough. So now our particle has also a draw method there. Okay. Now vectors. This is something people find scary. Some people find very scary. It's not very scary, it's very easy. This is a particle. It's at 30 and 10. These are the coordinates. It's exactly the same as a vector defined at 30 and 10. So vectors start in the origin. They can either be defined by angle and magnitude, so angle and how long they are, or the tip point. They are equivalent. They are actually, you can write bijective function that transforms from one to the other and back. If you want the object to move, let's say I want the object to move by this vector, you need to know how to add vectors. And you may have learned in school that to add two vectors like that, you move one on top of the other, you make this parallelogram, and then you draw the resulting vector 30, 11. But what it really means from algebra point of view, 30 plus 0 and 10 plus 1. So 30 and 11 is going to be what happens when you add the vectors. Okay. Now, here, I'm going to have to change our code a little bit. So what I'm going to have is particle defined as a new particle. So this is where I'm instantiating my particle class, and I'm going to give it a location vector, which I already have here, and also a velocity vector. And let's say that the velocity vector is going to be just between 0 and 1, but still random. If I put it very high, then immediately when they move, they go out of the canvas. They will go 300 pixels away, and I don't see them anymore. But if my random value is between 0 and 1, some will go faster, some will go slower. Yeah, and the rotation is also going to be random as a result. So our particle is going to have a location and a velocity. Okay, and I want to keep track of these particles somehow. So I'm going to define here an array called particles, like that, and I'm going to push it, the new particle, to it. Pushing means I add to the end. So our particles will be an array with 50 elements that have random location to begin with and a random velocity. Okay? I'm going to make this particles array as a global variable, because I want to inspect it now in the console and show you how you can do that, just to see if this works. And I'm going to remove this console log from there. I save the file. I refresh the page. Nothing happens here because I'm not drawing anything anymore. I removed that code. But particles is an array. It's a global variable. And each particle here has a location, which is a random location, and a random vector. Okay? Now, if I want to redraw them again, I could do, for example, the same thing. Either just do this for loop, or now, because the array is full, I know its length. And I can say particles of I dot draw. So this is practicing calling the draw method from here, which expects still where to draw it on our canvas parameter from that. So now what happens is that these particles are being drawn, but they are not moving. So what I want to do is again make an interval as before, set interval, and in this interval, very similar to what I did in the previous interval, clear the canvas first. Okay, clear the canvas first. Move the particles. So how do I move the particles? I go to each of them and I say that the location has to be modified by the velocity. I would really like to write this, but I don't know if it's possible. I have no idea if I can overload operators in JavaScript. So instead I need to create a function, add vectors. I need to add the current location of the particle with the current velocity of the particle, as in the PowerPoint slides. And our add vectors is very easy. So add vectors v1, v2, it's going to be, I need a new vector to keep the result, and it's going to contain v1 of 0 plus v2 of 0, and v1 of 1 plus v2 of 1. So quite easy, and I return the new vector. More or less like in the PowerPoint, you could see that you could just add those two things. And now the location should change with the velocity. Or I'm going to get errors. Yes, I forgot a closing parenthesis. This one here needs to be closed here. And more errors. Wow. Errors. Cannot read property 0 of undefined. I'm sorry? Add vector. Oh, what? I'm going to put a breakpoint in this function. And the parameters are 0 and 1, undefined. Okay. Oh, I'm sorry. In these particles, I called it vector instead of velocity. So I was looking for vector, which is undefined. Now it is probably, hopefully, going to work. I remove the breakpoint, I refresh, and my particles are all over the place. So this can be also an effect like dust particles going around or whatever. If you want them to go also the negative direction, you need to make sure that your velocity also has negative values. To have that, you just remember that the random is between 0 and 1. So if I'm going to do minus 0.5 to each of them, now it's going to be between minus 0.5 and plus 0.5. So I save it, and now they go like that, and they disappear.
Excuse me?
Yes?
What was the reason to use the vector?
So, okay, vectors are a tool for doing algebra that makes it easier to implement things. This is one thing, the addition, but I would like to present something more, like other vector operations. So you can easily implement functions using vectors that look like something. So you could just use points or distances to calculate these things. But if you study vectors more, you will see that if you understand more operations with vectors, you can do more impressive things very easy through code. So that's why I would like you to learn a little bit about vectors. I'm going to do something really quickly now. So probably it will confuse everybody. But I want to give you something to look at like a homework. I will try to explain what I'm going to do, but 10 minutes. Yeah? Okay, in short, what I want to do, I have the particles, right? I'm going to have a sun. I want the sun to attract particles like gravity works. I want the particles to become planets, and I want them to maybe orbit the sun. To do that, you need to learn vector subtraction. So the sun is going to pull on each particle with a force. Vector subtraction works in mysterious ways. Okay, vector subtraction, it actually is the same as 150 minus 30 and 150 minus 10. So that would give me this direction here, and my particle is going to move there. Okay, so I could calculate by subtracting vectors the vector I need to move to the sun. Okay, sounds very easy. Var sun. I put it in the middle of the screen. Okay. Now, with the sun in the middle of the screen, I maybe also want to draw the sun so that we see it somewhere. So let's put, for example, yeah, I'm going to draw a regular polygon. After I am going to draw all the particles, I'm going to draw one regular polygon at the sun location, a bigger polygon, so let's make it 10, and number of lines, let's leave it 8, maybe it looks good. So refresh the page. This is our sun. It looks a little edgy. I'm going to make it 16 here. Fair enough. Now, need to calculate that vector from the location to the sun location. So I mentioned before that I need a function for subtracting vectors to do that. Subtract vectors, it's one minus the other. Okay? This is the easy part. So if you have these functions for adding, subtracting, then vectors should become quite easy if you know the intuitive definition of them from the PowerPoint slides. Now, for each particle, I need to get the vector to the sun. So the vector that the sun is pulling on the vector, on each particle. So that's going to be subtract vectors from the sun vector, so from the sun to the particle's current location. This is now going to give me, let's call it sun vector. Okay. Now I could move the particles with this vector, but if I do that, it's going to move immediately to the sun location. It just teleports to there. The sun is going to pull slowly on the vector, on the particle. Too fast. You need a function to normalize the vector. Normalized sun vector. I will explain what it is. Normalize sun vector. To normalize a vector, it means that whatever this vector is, it's going to be 120 and 140, right? This subtraction. These are big values. Normalizing means bring them to 0, 1 scale. You divide this so it becomes the length 1. So I need to calculate the length of this red line and divide my 120 and 140 by that length. Technical, but not overly complicated. Then I have a unit function there. Normalize vector, vector. So, what is the length? Let's call it distance. So that the distance, how long that red line is. Or also called the magnitude. Well, it's actually Pythagorean's theorem, but the vector is centered at 0, 0, so it's going to be 120, 140, 0, 0, and it creates a triangle there. I need to calculate the hypotenuse. So magnitude is going to be the vector's 0 coordinate squared plus the vector's 1 coordinate squared square root of that. So this is Pythagoras' theorem, but I don't need to subtract 0 from any of the terms. This is the magnitude. And now to modify, I'm going to say vector of 0 divided Okay, let's just copy this from here. So our new normalized vector is going to be vector of 0 divided by this magnitude and vector of 1 divided by the magnitude. And this is what we return. We will get through this more in detail next time if you want. So it's not you don't need to be scared. I just want to show what you can do with just a little bit of vectors. Okay, and this should really be its own function. So get magnitude of a vector, function get magnitude. I'm trying to keep as clean code as possible. It is a little bit messy, but some global variables here and there, but I'm pretty happy with what happened today. Okay, so our normalized sun vector, we have that. We could actually move now, so our location vector of the particle is not going to move just with that velocity from before that each particle had in the beginning. It's going to also move with our normalized sun vector. So what we have to do is modify the velocity of the particle. So if the sun is pulling on a particle, particle is moving, it has a speed, but the sun is moving even more. I'm going to add to the speed, so calculate the new velocity for the particle is going to be the old velocity for the particle plus whatever the normalized sun vector is telling me. So move towards the sun a little bit. I really hope this works because my brain is hurting. Aha! Look at them go. Wow, 436. Normalize is not defined. Normalize vector. Function name was wrong. V1 is not defined. Wow, I'm on a roll. See what happens if I don't run after any small change. This happens. Errors after errors after errors after. Cannot read 0 of undefined. This is horrible. I'm sorry? No, it's something else. Come on, time is running out. Okay, V2 is undefined again. Where is that? This maybe is undefined. Normalized vector. Oh, I'm sorry. The normalized sun vector is not a property of the particles. It is just a variable I define here. Too fast, but I need to give it to you as a homework. So, okay, just how the universe works, right? No, it's not. Okay, but something very interesting is happening here. Okay? I have to slow this down. So animate particles, set interval. Oh, this interval has, first of all, no time, so I think it maybe uses a very fast one. Okay, they move to the sun and they jump back. And they move to the sun and they jump back. It's like a yo-yo. Each particle is like a yo-yo. It's accelerated towards the sun. It passes through because it has a high speed. And then at some point the sun starts to pull back. But that's not how gravity works. Okay? If you Google Newton's laws of gravity, you will find the universal law of gravitation says that the sun starts to pull less on an object when the distance to the object gets bigger. If you're away from the sun, it's not going to pull as much. And the ratio is actually squared. So The more you go, even stronger even weaker it gets. So, final thing, just please bear with me one more minute. I hope it's gonna get done. G is gonna be our gravity pulling force. Then here, instead of using this normalized sun vector, I have to calculate the force. So sun force vector is going to be G divided by, magnitude of the vector. I need to know how far is it going to be from the sun, and squared. So this is how the formula looks like. And this scalar has to be multiplied by our normalized sun vector. But I don't have a function to do that. Scale vector, normalized sun vector, by G divided by the magnitude squared. So last thing, scale vector, this should be quite intuitive. Scale vector with a scalar, I'm going to say here multiplied by the scalar. So both of them get multiplied. And please run. No, it doesn't run. I'm sorry. I need to use the sun force vector here instead. I calculated it, but I never used it. So the sun force, instead of what we had previously, it's generating errors. Property 0 of undefined again. I think I will give up.
You didn't return it.
I didn't return it.
Yeah.
Thank you. Too slow. Too slow. 0, 10. Okay, what is happening here? Particles are moving, some are starting to orbit, some are being slingshotted away from the sun. You may hear about this gravity assist when you watch some sci-fi movies. But more or less, this is a way to simulate how a universe works. And yeah, and you can experiment with different distance functions, or you can experiment with different amounts of gravity, and you will have very different effects happening in this place. Now, collisions don't work here. I would expect something very close to the sun to have a collision, make the sun bigger or whatever, some artifact. But yeah, I'm sorry it took so long, but I wanted to write all these functions for manipulating vectors. We will get through them, at least the necessary ones. And yeah, so here, for example, if you put the gravity strength, a higher strength for the gravity, then we will probably have some weirder artifacts happening. Luckily, this doesn't happen in our universe. Okay. You may also think, what happens if our magnitude is not squared? So if Newton would have discovered that magnitude is cubed, okay? So if magnitude would be cubed, this would be another universe, a universe where another physical law exists, then this is what would happen there. Points that get really close get slingshotted really, really quickly, and they don't seem to become orbits. If you're too far away, you're completely ignored. It's a very weak force. So solar systems wouldn't form in such a universe. This is the kind of stuff that scientists do, but the simulations are much more accurate. okay, one more thing. Here we're only calculating the force from the sun. Each planet also pulls on the sun. I'm not calculating that. So it could be improved. And also each planet moves on each other planet. So to make a good simulation, even though this looks relatively like what happens in our universe, it's not a very trustworthy simulation. Even though with time planets do stabilize in this and they will form elliptical loops around the sun.